Hello. Welcome to the second part of our nail penetration test series, where we will discuss the data we obtained last time, as well as some of my experiences as a graduate student. As a reminder, during the first part, we learned a bit about how a battery operates and later conducted two nail penetration tests with identical batteries on two different platforms, one plastic and the other aluminum. The only difference between the two tests was the plate upon which the battery was mounted. Driving a nail through the battery led to an internal short circuit, releasing lots of energy in the form of heat. The temperature of each battery was monitored via an infrared camera over the course of the test. Here, our goal is to analyze the quantitative temperature data from each battery as a function of time. It is important to observe that both batteries start and end at the same temperature, meaning that the differences in the plots cannot be attributed to any sort of offset between them. Let's focus on three separate behavioral sections for each data set: temperature increase, peak, and decline. Both tests display similar initial behavior, with a fast increase until reaching a sharp peak. This regime corresponds to the onset of the electrochemical reaction in our battery that generates heat. Electrons travel from one side of the battery to the other, allowing for a rapid release of the energy contained within the battery as they recombine with lithium ions at one of the electrodes. The heat produced here is conducted into the liquid electrolyte and can cause it to burn. As the rest of the electrolyte heats up via conduction and convection, the battery can catch fire. In the battery industry, this type of uncontrolled energy release is called thermal runaway and has previously appeared in the news surrounding Samsung Note batteries. One thing we can see from the data is that the battery on the aluminum plate seems to heat up faster than the one on the plastic plate. Before we draw too many conclusions, we need to acknowledge that it was not possible for me to exactly replicate the way the nails were moved in each battery. I did my best to keep that process as similar as possible, but there is still some ambiguity with respect to the nail movement. If we assume, however, that it was similar enough between the two tests, the fact that the aluminum peaks first makes sense. Heat generated by the short circuit leads to a combustion reaction for our electrolyte, which in turn releases more heat. The aluminum plate, which has a much higher thermal conductivity than the plastic, will be able to spread that heat produced at the center of the battery from the nail penetration much faster. As the heat spreads, the chemical reaction propagates, releasing even more heat. These factors cause the battery on the aluminum plate to heat faster than the one on the plastic plate, reflected in the steeper slope at the beginning of the experiment. This is similar to what happened in the warm egg experiments that you previously conducted. As the thermal conductivity of the liquid in which the egg was placed increased, the liquid warmed faster. In those tests, the thermal conductivity was affected by the amount of dissolved ions in each solution. If you go back to your egg data, can you identify the liquid with the highest and lowest thermal conductivity? In our nail penetration tests, the heat from the middle of the battery was able to spread faster because of the higher thermal conductivity of the aluminum. Now let's focus on the peak. From the plot, it is clear that the aluminum battery's peak temperature is lower than that of the plastic battery. What's more, the peak temperature regime of the plastic battery is significantly longer lived. Why might that be? Again, it's a question of the very different thermal conductivities for plastic and aluminum. We can think of thermal conductivity as the property of a material that dictates how well it transfers thermal energy. The aluminum is very good at moving thermal energy away from a hotspot and distributing it evenly across the plate, eventually radiating out that heat to the surrounding air. As the battery heats up, the thermal energy it emits is readily transferred to the aluminum, which quickly spreads and dissipates it. Plastic is not as good, meaning that hotspots stay hotter for longer. The heat coming from the battery very slowly transfers to the plastic, allowing it to accumulate for longer. That buildup of thermal energy results in a sustained higher temperature for the plastic battery. These points now help explain the temperature decline section of each plot. Once again, potentially different nail movements in each penetration test can make comparisons a bit ambiguous. However, If we look at the temperature behavior right after the peak, it is clear that the aluminum plate lost heat much faster than the plastic plate, as evidenced by its steeper negative slope. The plastic test has a flatter slope as its temperature gradually decreases. Overall, the data shows that the plastic has a far worse thermal conductivity as compared to aluminum. The fact that it can't quickly spread its heat or transfer it to the surrounding air is evidence that the plastic is not suitable for applications that require efficient heat transfer. As a material scientist, it is my job to ask why. What is it about aluminum that makes it better at conducting heat than plastic? The answer lies partly in their very different atomic structures. You can think of the structure of aluminum as a network of balls attached to their neighbors by stiff springs. If I shake a ball on one side of the network, it will take next to no time for that motion to be felt on the other side. Plastic, unlike aluminum, is composed of long chains of molecules that are all mixed and tangled together like a giant bowl of atomic spaghetti. If I shake a noodle on one side of the bowl, there will be little to no sign of that movement on the other side as the noodles easily slip and slide past one another. The shaking motion is an analogy for the thermal energy that excites atoms and causes them to vibrate. Vibrations travel much faster through the aluminum network of balls and springs because they are strongly attached to one another in 3 dimensions. The balls correspond to the aluminum atoms while the springs are the bonds between them. The ability to quickly propagate vibrations, and therefore thermal energy, is part of what gives aluminum such a good thermal conductivity. The long, weakly bonded chains in the plastic hinder its capacity to transmit heat, making it a poor thermal conductor. The ability of electrons to flow in between aluminum atoms also contributes very significantly to its thermal conductivity, but that is beyond the scope of this discussion. I'd like to transition a little bit more to talking about what the life of a graduate student actually looks like. Personally, I'm very adventurous and like to spend a lot of my time outdoors. I like to go surfing, rock climbing, and playing water polo. Science is a passion of mine, so I like to also spend a lot of my time volunteering to share science with other individuals. In the current times in which we find ourselves, these outreach events have been much more remote, like this one. As a graduate student, and specifically as a doctoral candidate, I'm paid to take classes and do research. If I were to be pursuing a master's, I would have to be paying tuition, but as a doctoral candidate, I get paid to take classes and do this research. While I am now entering the second year of my graduate studies, I cannot say that I always expected to make it this far. It is only through the support of my family and friends that any of this became possible. My mom is French and did all of her schooling in France, while my dad is Moroccan, but immigrated to France after finishing high school. They met in France and immigrated to San Francisco in 1997, where I was born shortly thereafter. Growing up as a first-generation American, I spoke French at home and English at school, resulting in some difficulties in my early schooling. Applying to colleges was also kind of a difficult process for my family. My parents did not have the experience that other families had in the higher education system in America, and as such, they didn't really have that experience to help me with preparing my applications. Talking to college counselors at my high school was an instrumental part of preparing my applications, and if you have any trouble in that process, I would highly recommend you go interact with them and seek their help. Throughout my life, I've dealt with a number of setbacks, both academic and personal. And I would say that in the end, leaning on the support of your loved ones and acknowledging the positive and formative power of failure is really the only way to move past those setbacks in pursuit of your goals. Because my job is mostly to conduct research, one of the places I spend a lot of time is my research group's lab. There, my groupmates and I conduct experiments to better understand the electrochemistry and physics of a variety of battery materials. As you may well know, lithium-ion battery technology today is far from perfect. Electric cars don't have the same range as fossil fuel-powered cars, and phone batteries never last as long as we'd like. In my group, we make batteries from scratch, test them, and use a lot of different techniques to elucidate how they function and degrade. Then, we use that information to suggest ways to improve them. Importantly, we publish articles in scientific journals designed to share that information that we learned with other research groups so that they can build on our progress. Let's take a brief tour of the lab and look at a couple of instruments that we use in our research. This is a high-energy planetary ball mill. This instrument is used for synthesizing materials and mixing or grinding powders. Inside, 2 jars are diametrically opposite from one another and filled with powder and lots of small balls. As the jar begins spinning within the instrument, the balls inside start colliding with one another with some powder stuck between them, forcing the materials to either react or just reducing the size of the powder particles. This is a fume hood. Fume hoods are important tools for researchers who work with volatile chemicals that go into the air. Because we do not want to breathe in those chemicals, we use fume hoods to suck up the air so that the fumes do not escape the hood, protecting us from inhaling them. Inside this fume hood, you see a tube furnace. Inside the glass tube of the tube furnace are some chemicals that we have mixed together. As they are exposed to the high temperature of the furnace, they react to form the compounds we want to make. This furnace is currently operating at 750 degrees Celsius. In the back of this fume hood, you can see a microwave. Surprisingly, this is a standard microwave oven, exactly the same kind as somebody might find in their kitchen at home. Just how a microwave heats up your food, it can heat up precursors for a chemical reaction to make our materials. Pretty incredible stuff. The glove box is one of the most important tools of our research lab. Many of the chemicals we work with in our lab are sensitive to air and will react or degrade when exposed to it. A glove box allows us to handle these materials in a closed, inert atmosphere of argon gas. The oxygen and water content inside are kept below 0.5 parts per million. To give some perspective, ambient air is 209,500 parts per million oxygen and 25,000 parts per million water. We have a press for making pellets of powder on the left, a scale in the middle, and another press for making batteries on the right. Batteries need to be assembled under air-free conditions because many of their components are very susceptible to being corrupted by air. This is a battery cycler. We use it to charge and discharge the batteries we make in order to understand how they are behaving electrochemically. It is important to see how much charge we can extract from our batteries and how repeatable that process is to characterize the performance of the materials we are interested in. In front and on top of the cycler, you can see some of the batteries that are hooked up at the moment. As you can see, we have a few different ovens. This one is capable of going to higher temperatures than the earlier one. This concludes our lab tour. As you can see, battery research requires highly specialized equipment for synthesis and testing of battery materials. My own research seeks to replace the liquid electrolytes in today's common lithium-ion batteries with other solid compounds that are capable of conducting lithium at comparable rates. Similarly to how materials can conduct heat or electricity, some others can conduct ions if a voltage is applied. As I previously mentioned in the discussion of thermal runaway, in the event of a short circuit, liquid electrolytes can catch fire. While these events are exceedingly rare, the enormous prevalence of lithium-ion batteries in today's world means that statistically, a catastrophic failure can still happen. The materials I work on are incapable of burning and therefore would make electric vehicles and everyday portable devices much safer. I try to design and understand materials that are made from common elements that are readily available in order to make this technology environmentally friendly and broadly accessible. This research, however, is only one thrust in the vast global ecosystem of energy storage research. Many other research groups are looking to alternative methods, like using hydrogen as a cleaner fuel, or simply pumping water up a hill to store energy using gravity. Other research thrusts focus on making certain processes more efficient to reduce waste energy. Because waste energy is often released in the form of heat, designing materials with the desired thermal conductivity properties is incredibly important. I encourage you to research some of the different energy generation and storage technologies that exist today. If you are interested in thermal conductivity, you will likely have fun learning about thermocouples. I won't give you any spoilers, though. I wish you the best of luck for the rest of your school year. If you have any questions or want to follow up with me on some of the topics we addressed today, feel free to contact me. Thank you for your time and attention.